This is standard 8FA1. We're dealing with functions. Here we're going to understand that a function is a rule that assigns to each input exactly one output. That's the definition of a function. Now, what we've got here is basically a little function machine where you put in something and then you get out something. Think of it like a little factory. What if I had a little factory sitting over here and I wanted to make orange juice? So what I put in would be oranges, and what I would get out would be orange juice. Every time I put in oranges, I would get out orange juice, a little factory here to make orange juice. Well, this is essentially a little factory with rules for math. Let's say that we want to put in numbers and we want them to go through the equation. Y is equal to negative 2x plus 1. So I'm putting in x values, going to plug them in here, and I'm going to get out y values. Let's see what we could do. Let's see the different things we might put in. Let's say we put in an x value of negative 3. If I put in negative 3, here's what I would get to my y. Y is equal to negative 2 times our x, which is negative 3, plus 1. Negative 2 times negative 3 would give me positive 6 plus 1, which is 7. So when my x is negative 3, when I put in a negative 3, I get out 7. What if I put in another number? Let's pick another number. What if I put in 0? Okay. If I'm dumping 0 in, put 0 here in for x, what would I get out for my y? Well, let's see. Our equation is y is equal to negative 2x plus 1. So y is equal to negative 2 times 0 plus 1. Negative 2 times 0 is 0 plus 1, which gives me 1. When my x value is 0, my y value is 1. When I put in the x, when my input is x, put it through this rule, I get out a 1. Now let's try another number. What if I go with 2? Okay, let's plug it in. We're looking for the y. Our x is 2. Y is equal to negative 2 times 2 plus 1. Negative 2 times 2 is negative 4 plus 1, which is negative 3. When I put in a 2 for my x, my y is negative 3. If my input is 2, my output is negative 3. Notice, whenever I put in a number, what I get out is unique. If I put in negative 3, I can't get out a different number. If I put it through this, if I put negative 3 in for x, there's only one number that I can get back out, and that would be 7. If I were to put in negative 3 and I got out 5, it wouldn't make sense because my function says if I put in negative 3, I get 7. So the rule of a function is that it has exactly, for each input, there's exactly one output. If you want to know if something's a function, look at your x, make sure that there's no more than one y value for that x. Now, let's try another function. Let's do another function. What if you've got y is equal to 1/2 x plus 3? Let's do the same thing here. We've got some x's and some y's, and see we're creating our coordinate pairs. You could plot these if you needed to. What if my input, what if my x value here, or I could give it a different letter, I could give it y and z, I could give it, call it whatever I want to. What if my x value here was 2? Okay. Then we put it into our equation. Y is equal to 1/2 times 2 plus 3. 1/2 of 2 is 1 plus 3, which gives us 4. This tells me if I put in a 2, I get out a 4. Okay? What if I have a 0 here? So see, this point would be 2, 4. That's my coordinates. What if I put in a 0? Okay, this time instead of a 2, we're going to put in a 0. And see what we get out. Okay, y is equal to 1/2 of, put in a 0 for our x, plus 3. Half of 0 is 0, plus 3 gives me 3. If x is 0, if my input is 0, my output is 3. How about if I use 6? Y is equal to, and we use our equation here, we're going to put in a 6, 1/2 of 6 plus 3. Half of 6 is 3, plus 3 gives me 6, right? So if I put in a 6, I get out a 6. My coordinates would be for this one 6, 6. 2, 4, 0, 3, 6, 6. Okay? And these would be coordinates that we could plot. This is a linear equation in this case. But functions don't have to be linear equations. Functions could be other things. What if I've got, let's call this A is equal to m squared. Okay? A is our input. M is our input. We're putting in m, and we're going to get out our A. A is our output. M is what you're putting in. A is your output. Okay? Now, what if I put in a 0? A is equal to, and our equation is m squared. 0 squared. 0 squared is 0. So I know that I've got one coordinate that goes through 0, 0 if I plot this. What if I try 2? Okay. A is equal to m squared, 2 squared, which is 4. So this coordinate would be 2, 4. What if I put in 5? A is equal to 5 squared, and 5 squared would be 25. Okay? If I actually plotted this one, it's going to look like this. We start at 0, 0. We'll go over to 2, and we'll be going up 4. We go over to 5, and you'll be going up 25. Be way up here. You're looking at something that's going to curve, right? Going to go up like that. So that's not linear, but it's still a function. Functions are also used whenever we're talking about real-world situations. And I want to do one real-world situation with you. And I'm going to erase this one here so we can do it. What if we're talking about the distance that a car travels? And let's say we're looking at a car that is going 50 miles per hour, an average of 50 miles per hour. Well, if our equation is distance is equal to 50 miles per hour, see, that's our rate, our unit rate, or our rate of change, you could call it, 50 miles per hour times the number of hours. Okay, so we'd be inputting our hours, and we would be outputting the distance that we had traveled. What does this mean? It means this. If my hours are 0, I've gone 0 hours. Doesn't it make sense that I will have not gone any distance? 50 times 0 would give me 0. At 0 hours, I've gone 0 miles. There's my coordinates for that one. How about after 1 hour? The distance would be 50 miles per hour times 1 hour, which would mean I had gone 50 miles. This point, if I'm going to be plotting it, would be 150. What if I've traveled 2 hours? The distance would be 50 miles per hour times 2 hours, which would give me 100 miles. And that would give me 3 points. If I wanted to plot this, I could easily plot it. Let's see, this is, our first one is hours. This would be hours. Our y-axis would be miles, distance. 0, 0, okay. After 1 hour, let's say we've gone 50 miles, right there. Let's make this 100 miles right here. After 2 hours, you would have gone 100 miles. And what you plotted here is a linear equation. Now, what we have to understand is whenever we have a function, the x does not repeat. For each x value, there's a unique y value. If I put in, up here on this one we just did, if I put in 1 hour, I'm going to get out 50 miles. If I put in 2 hours, I'm going to get out 100 miles. If I put 2 hours again, I'm not going to get out something different because 50 times 2 is 100. I would never get a different value. I'll look at my x, I'll look at my input. My input can only have one output. I could not have a point that was something like this, 2 and 150, because 2 is already with 100. I couldn't have two different points. Could not have two different y values, two different outputs for my input. Select all of the following that represent functions. If you've got a function, each input has one and only one output. In other words, your x's cannot repeat. Let's look at this and see. This input of 2 has an output of 5. Are there any other inputs of 2 here? No, I have 3 and 5. This is a function. Each one of those inputs has just one output. 2 has a 5, 3 has a 10, 5 has a 26. Let's look at this one here. Here are our inputs, here are our outputs. -3 just has one output, it's 2. You go, well, wait, there's another line going here. That's 4 that has that output of 2. The inputs can't have two outputs. The inputs can't repeat. 3 has one output, -1 has one output, 1 has one output, 4 has one output, 5 has one output. Each of those has one output. This is a function. Another way to look at it, look at your x's, your inputs. Did anything repeat? There's no repetitions on our x's. Now look at our input here. Is there anything repeating? Look right here. Nope, not there. Here, 6 and 6. Erase that other one so that's not confusing for you. On our x's, notice we've got 6 repeating here and we've got 6 repeating here. If the x is repeating, it is not a function. Now I'll show you why. The way to tell if something is not a function, each input can only have one output. The 3 has 5. Here the 6 has 8, but here the 6 has 11. You can't have 6 with an output of 8 and 6 with an output of 11. Okay, that does not work. Okay, if you put 6 into your as your input, you can't get out 8 one time and 11 the next. So this is not a function. For the input of 6, there are two different outputs, 8 and 11, so it is not a function. Now the other part to this standard is this. You need to understand that a function is a rule that assigns to each input exactly one output. So essentially when you graph it, you've got a rule that assigns just one input to exactly one output. Okay, we've talked about this. There's another way to check it. What if you've got something plotted? We know that each x value can only have one y value. We use something called a pencil test or a vertical line test to prove whether or not something is a function. Just like we did over here, where we were proving things were a function by checking their x values to see if the x value repeated. We're going to do the same thing over here. We're checking to see if the x value repeats anywhere by running a vertical line over the graph. I've got a vertical line here. I've got a graph. Let's see if it hits any 2 points at the same time. Grab it. Notice everywhere I go across this line, if I take it like a vertical line, as I'm going left to right, it only crosses 1 point at a time, never more than 1 point at a time. So therefore, this is indeed a function. Okay? So we're going to write that on there. This one's a function. I'm going to put f as a function. This one's a function. Okay? Let's try this line. That one was going down. This one's going up. This one's slope is positive. Let's run our vertical line, or pencil if you want to, over it. Is there anywhere where those two lines intersect at more than 1 point? No. See, everywhere you've got it, it's intersecting at just 1 point. Went all the way across it. So that is indeed a function. Let's put f by it. This one's a function. Let's do this one and let's see if it intersects anything more than 1 point. No, it's just going across it at 1 point. This vertical line is only going across it. My pencil's only touching it at 1 point all the way across. So that's a function. Let's keep going and see if any of these are not functions. How about that? Let's try this. Let's try this one. Hold on. All right. Let me see where my pencil is. Well, think of it this way. What if I run this line across it? We're getting there. What if I take my line and I run across it here? There's only one place I touch each one of those line. That's line. How about this one? There's only 1 point where I intersect the line all the way around. What about here? There's only 1 point that I intersect the line at every place where I go. How about this one? There's only 1 point where I intersect the line everywhere I go. All of these are functions. Let's go down here at the bottom. I've got a couple of others that are not functions that I want you to see. Okay, we're going to try to grab our pencil and bring it with us. No, we don't want that. We don't want a pencil. Okay. Now we're going to be able to see if these are functions or not. Hold on, let's get it farther down. Notice this is not a function. As I go across, please notice that I've got 2 spots that this is actually touching the line. 2 places this is intersecting the line. So this is not a function. Let's try bringing our function line farther over. If I were to do one across each one of these, none of these are functions because whenever I take a straight line across them, I'm going to hit this at more than 1 spot. See if we can get this to let you see it better. grab this and bring it over here. In each case, this is touching it at 2 points. Everywhere along here, it's intersecting that circle at 2 points. How about this line? Notice when I get right here, I'm intersecting that at 3 points. That red curve, I'm intersecting it at 3 points. Here, I'm intersecting it at 2. Okay, so that's more than 1. It can never intersect it at more than 1. Here, it's intersecting at all points, definitely not a function. And here we're intersecting at 2 points all the way across. So this is not a function. All the ones at the bottom are not functions. The one that's at the top are functions. Now, one other thing we need to understand in the standard is that the graph of a function is the set of ordered pairs consisting of an input and the corresponding output. Whenever I graph a function, whether it's linear or not, what you've got is an input and an output. On this chart, let's look for the input and the output. The input is our x. This says if we've got an input of -3, then what is our output? Let's try to figure out what our output is. We can look on the chart and see on most of these. When our x, because here's our x-axis, when our x is -3, our output, our y, is -2. So when our x is -3, our y is -2. That's what we've got plotted. What about when our input's -1? Our x is -1. When our x is -1, our y is 2. How about when our x is 0? When our x is 0, our y is 4. How about when our x is 3? Gee, we don't know. We might need to write a linear equation, so this is a line, and plug in our input and figure it out. Well, let's write a linear equation. Y is equal to mx plus b. We know our b is our y-intercept, which in this case is 4. We need to find out what our slope is. It's our rise over our run. And we can calculate it here. Rise, in this case, is up to, run is over 1. My slope is going to be change in y over our change in x, which is 2 over 1, rise over run. 2 over 1 is 2. So here's our equation. Y is equal to 2x plus 4. Let's plug our 3 in for the x. Our input is 3. Y is equal to 2 times 3 plus 4. 2 times 3 is 6 plus 4 is 10. Our y is 10.